So our buddy Tiffany here, we have a function p prime of t, that's in the table, t is in hours, and we're going to do a little bit of work here with Riemann sums. So for the first one, it says, use a right Riemann sum with 3 subintervals to approximate the area between p prime of t and the t-axis from t equals 0 to t equals 5. Include units of measure with your answer. What does this answer represent in the context of the problem? Okay. So just like any problem in calculus, 2 things overall. One of them is you want to keep reading and rereading the problem. And the second one is while you're working, you want to kind of go back and forth. So what we've talked about with Riemann sums is that it really is best always, if you're doing a Riemann sum, especially as a beginner with Riemann sum, to start off with the, sorry, that's not very clear. There we go. That picture seemed to do the trick. All right. Considering the inputs. So from the table, and I encourage you to have also open on your screen the problem. According to the table, from the interval 0 to, or the interval 0, 5, we want to make 3 Riemann sum rectangles. Now, you may be looking at this right now and you may be sorely confused because what we've done so far with Riemann sums has been talking about uniform bases, and uniform bases are impossible here. Look at this. If we were to do a equal base length for all 3 rectangles, we would do from 0 to 5 is 5 units, divided into 3 equal pieces, that's 1 1/3. So if I start at 0, my interval is going to end at 1 1/3. And then my second interval is going to go from 1 1/3 to 2 2/3. Then my last interval is going to go from 2 2/3 to 5. That's impossible. Why is that impossible? Because this is all of the information I have about the inputs of this function p prime of t on the interval. So we didn't really do much with this calculation-wise, but we are today going to be emphasizing that Riemann sums can be done with non-uniform bases. And we especially want to do that here because we do not have the values that we need. Again, we're doing a right Riemann sum, and if we were using equal bases, we would go from 0 to 1.3 repeating, 1.3 to 2.6 repeating, and 2.6 repeating to 5. That's impossible. We don't have a function value at 1.3. We don't have a function value at 2.6. We don't have all of that information that we need. The 1.3 is taking the total distance from t equals 0 to t equals 5, which is 5 units, and dividing it into 3 equal pieces because I need 3 rectangles. So that's where I'm getting the 1.3 from. I'm taking the total, dividing it into 3 equal pieces. So how does a Riemann sum work if we have oh, I suppose that's right. Let's not talk about my arithmetic. On to the calculus, which hopefully I'm capable of doing. For each of the 3 rectangles, we are going to be calculating a base and a height. So the first rectangle, the base of it goes from 0 to 2. So that is a base length of 2 units. Now, This next part should feel more familiar. We're doing a right Riemann sum. So if we're going from 0 to 2, we choose the rightmost value 2, and that value in the function gives us the height of that first rectangle. So we're going to calculate the value of that first rectangle by doing the base 2 times the height, p prime of 2. The second rectangle goes from 2 to 4, which is a base length of 2. The height, because we're doing a right Riemann sum for the interval from 2 to 4, we choose the right side value, which is 4, and substituting that into the function, p prime, gives us the height at 4. So we've got one rectangle with a base of 2, a second rectangle with a base of 2. The third rectangle has a base of 1. How come? Because we're going from 4 to 5. That's only 1 unit. The height is going to be on the right-hand side from 4 to 5, or 5. So my first rectangle is going to be base 2 times height 30. The 30 comes from looking at the table at 2. Second rectangle, base 2, height 54. The 54 comes from the table, looking at the table value at 4. The last rectangle, base 1, height 26. The 26 comes from looking in the table and determining that when t is 5, p prime is 26. So if I multiply these, add them up, I get 194 people. Where do I get people from? Well, this is the same kind of idea, if you'll recall, when we did this earlier in the week on Tuesday. We talked about, with all of those wonderful graphs, that we have meters per second or feet per second times seconds. In this case, we have people per hour, and we're multiplying by hours. 30 is people per hour, 2 is hours. That gives us people. 2 is hours, 54 is people per hour, gives us people. Same thing here. So 194 people. Okay. So what I like to do after I feel like I've done something important in a problem, I like to go back and reread it and see what it's asking for. So if you reread example 4, it says we want to write Riemann sum using 3 subintervals from 0 to 5. We want to estimate the area between the curve p prime and the t-axis. And we want to interpret this in the context. So I've got correct units here. I've got my value. I showed my Riemann sum. I just need to do the interpretation. So check out this interpretation. This interpretation should feel somewhat familiar to you because we've been interpreting things in calculus for a while. Now it should also feel unfamiliar to you. So let's talk about the familiar part first. The familiar part is we have when, we have what's going on in the context. That should feel familiar to you. What's going to feel unfamiliar here is the when. The when is from 9 a.m. to 2 p.m. So what we're used to saying is at a singular time. That's because what we're used to looking at is the derivative, which happens at a singular time. What we're doing is we're adding up all of those amounts of change between 9 a.m. and 2 p.m. to get a total of 194 people. So from 9 a.m. to 2 p.m., 194 people saw Tiffany's picture. And I'll pause here for questions. Turning our attention now to example 5. So same file as before. This time, example 5, we want a left Riemann sum with 4 subintervals to approximate the area between capital P prime of t and the t-axis from t equals 4 to t equals 12. Then we're going to use correct units to interpret our answer in the context of the problem. If necessary, we can reread information about Tiffany so we know what the context is. But otherwise, let's jump right on in. So One thing I hope you will agree, even though we're doing something slightly different today with our work on Riemann sums, is that it's a really good idea to think about what's going on with the horizontal axis or the vertical axis or whatever the axis. Oopsie, wrong screen, sorry. There we go. So from 4 to 12, this is what we got. We have the same limitation we did before. That limitation is we cannot use uniform base measures. Check it out. If I were to use a uniform base measure, I would have to use a uniform base measure of 2. How come? Because if I go from 4 to 12, that's a total length of 8. If I divide that into 4 equal pieces, that's 2. So I'd go from 4 to 6, 6 to 8, 8 to 10, 10 to 12. The table, however, only gives us values at 4, 5, 6, 9, and 12. That means it's impossible to figure out what's happening at 8 and 10. Impossible. So I'm restricted then to the information that I have. But the information that I have lines up pretty nicely. My first rectangle is right here from 4 to 5. The second one is here, 5 to 6. Third one is here, 6 to 9. Fourth and final one is right here, 9 to 12. That was nice of the table creator to do that for us. Huh. Okay. Now we're doing a left Riemann sum. So what does it mean when we do a left Riemann sum? Well, when we're doing a left Riemann sum, for each subinterval, we want to be choosing the leftmost value. So from 4 to 5, that's my first one. My height is going to be at 4. 5 to 6, that's my second one, my second rectangle. We're going to do the height at 5. Third rectangle from 6 to 9, we're going to do the height at 6. Fourth and final rectangle, 9 to 12, we're going to do the height at 9. So each rectangle has a base and a height. So again, that first rectangle is going from 4 to 5. That means the base is 1. The height is going to use the leftmost value of the interval from 4 to 5, which is 4. So we'd substitute 4 into the function p prime. We're going to get that value from the table. The second rectangle goes from 5 to 6. 5 to 6, that's 1 unit. And then we choose the left value of those two between 5 and 6, that's 5. So p prime of 5. Third rectangle, we're going from 6 to 9 this time, and that is 3 units. The left value is 6, p prime of 6. And then the last rectangle is from 9 to 12, the fourth one. That's 3 units for the base. The height uses the left value, which is 9. So p prime of 9. So taking a look then at the table to get these values, the first rectangle is going to be 1 base height 54 plus 1 base height 26. Third rectangle, base 3 height 21. Fourth rectangle, base 3 height 44. Multiply, combine, we get 275 people. So there was a question earlier about approximation. And the Riemann sum is an approximation of the actual area. But I think because of how the problem is configured and where we're at right now, it's okay to write things the way we have without the approximation symbols. I will show you probably Tuesday, well, next week for sure, sometime how that's going to fit in with what we're talking about. So there's a really important math concept and notation piece we haven't studied. And then I think it makes a lot of sense to use the approximation symbol. Okay, so that was example 5. No, it wasn't. Make sure you go back and read the problem. We didn't interpret. So notice again, I'm going from 4, which is 4 hours after 9, which I'm pretty sure is 1 p.m., until 9 p.m., which I'm pretty sure is 12 hours after 9 a.m., 275 people saw Tiffany's picture. I will pause once again here for questions. Okay, so before I get into example 6, the question is there a disadvantage to using non-uniform base? And the answer is a yes, because when you're using a non-uniform base, the calculations are not quite as efficient. So we talked a little bit about last time how if you have a uniform base, you can factor that out and then just add all of your heights together. And then after you've added your heights together, you can multiply them all by the same number. So it's a little bit less efficient, and that matters a lot, especially when you're programming. So when you're programming something, you want to have your computer, the computation pieces, the CPU and the GPU, the processors, you want those to do as few calculations as possible. So when you've got non-uniform bases, that means you've got more calculations to do. But in terms of like finding a value, there's really no disadvantage to doing non-uniform bases. Which, speaking of, brings us to example 6, which is, again, a non-uniform base, just like we looked at. So if we were to do a non-uniform, or to do a uniform base, we'd look at the change in x, which from 0 to 12 is 12. And we divide that into 3 equal pieces. So our non-uniform bases would be 4 units each. However, we cannot do that for several reasons. One of those is we'd go 0 to 4, 4 to 8, 8 to 12. We don't have 8. But the other reason is we're doing midpoint this time. And 0 to 4, okay, we've got 2. 4 to 8, okay, we've got 6. 8 to 12, we don't have 10. So we're stymied. So what are we going to do? How are we going to make midpoints work out? Well, if we think a little bit differently about things, we're going to be able to get this midpoint thing to work out. So we're looking for 3 subintervals, but we're recharacterizing our thinking. We're looking for 3 subintervals that we can get midpoints for. So 0 to 2, that's going to be impossible, right? Because 1, we don't have, okay. 0 to 4, ooh. 0 to 4, we've got a midpoint. It's 2, right? 0 to 4, the midpoint is 2. Nice, okay. 4 to 5, can't do a midpoint there. We don't have 4.5. 5 to 6, we don't have 5.5. 4 to 6, though. 4 to 6 has a midpoint of 5. And you know what? While we're at it, 6 to 12. 6 to 12 has a midpoint at 9. So when you're doing midpoints and you have limited values, you're going to have to get a little bit, not creative, but you at least need to think like a bishop. You need to think on the diagonal. And you need to be considering different ways you can fit in the knowledge that you have with the information you're given, which honestly is pretty much all calculus is. But how is this going to work out here? Well, we're doing midpoints. So we're still going to have a base and a height. We're going to do 3 rectangles this time. So our first rectangle has a base of 4. Why does it have a base of 4? Because I'm going from 0 to 4. And then the height is the midpoint between 0 and 4, or 2. So P prime of 2. Second rectangle, we're going from 4 to 6. How long is that base? I know you just said 2. The height is going to be the midpoint between 4 and 6, which is 5. So P prime of 5. That third rectangle is going from 6 to 12. How long is that base? I know you just said 6. And then we're going to do the midpoint from 6 to 12, which is 9, P prime of 9. So this time, I'm going to go to the table to get my heights, and I'm going to get P prime of 2, which is 30, multiply that by the base 4. P prime of 5, which is 26, multiply that by the base 2. P prime of 9 is 44, multiply that by the base 6. And we get 436 persons, which we then interpret as going from 9 a.m. to 9 p.m. 436 people saw Tiffany's picture. I'm going to pause here for questions once again. Riemann sums is restricted to the rectangles. So using a rectangular approximation, there are other approximation schemes. Now, don't copy all of this down on your papers. What I want you to know is that besides the Riemann sum schemes with the left, right, and midpoint height rectangles, there is a trapezoid scheme, the trapezoidal rule. The trapezoidal rule for the same number of shapes is almost always more accurate than the Riemann sum. The trade-off, though, is, and please look on the right-hand side at that very small box. We're not finding the area of a rectangle, we're finding the area of a trapezoid. And the area of a trapezoid is the height times the mid-segment length, which you learned in geometry. Or as expressed here, it's b sub 1 plus b sub 2 divided by 2 times h. So to get more accuracy than the rectangles, we're trading off for a more difficult shape to find the area of, namely the trapezoid. So we're going to use the trapezoidal rule using 4 trapezoids, and we're going to estimate the area between the x-axis and sine of x as pictured here in example 7. So the trapezoidal rule is used to approximate. It's more accurate than the Riemann sum method with rectangles, but it's more complicated. So we're trading complexity for accuracy. This is not the only approximation scheme. There's another common approximation scheme which is no longer a part of BC calculus called Simpson's rule, which uses, instead of that diagonal line at the top, so everybody's looking at that trapezoidal picture with me, right? You're all looking at that. Instead of that, what it uses is a parabolic top. So that's the best parabola you're going to get with me using my mouse here, which is not exactly the most sensitive mouse. Anyway, I can say that because I didn't hurt its feelings because it's not sensitive. The Simpson's rule uses parabolic top, and you are again trading complexity for accuracy. So let's take a look at this trapezoidal rule. So the trapezoidal rule is going to use trapezoids. Now, you need to, if you've got this picture in your mind of trapezoids, change that to match the picture that you were presented with on the handout we just looked at. We're going to use trapezoids that have a flat edge on the axis. I'll show you what that looks like in a little bit. The other thing that's going to feel awkward about the trapezoidal rule is, you remember how it was the sum of the two bases? It's actually the sum of the two heights from what we did rectangularly speaking. So you may be confused about that, and why does that make sense? Well, a trapezoid, the two parallel sides, those are the bases. So we've got bases that are vertical. So it's a little bit kind of confusing and backwards. But I think once we actually do the calculations, it makes sense because overall it fits into what we were doing with the Riemann sum. So let's take a look here at a little bit bigger look at the shape we're talking about. So take a little bit of time, get that sketched in. We've got f of x equals sine of x. We're going from 0 to pi, and I've divided it into 4 equal pieces because it says equal bases. So how do I do the equal bases here? I, again, always like to think about the horizontal or whatever axis I'm looking at, and say if I'm going from 0 to pi and dividing pi, because that's how far it is from 0 to pi, by 4, I'm going to be going pi over 4 every unit. So my first trapezoid is going to have a base that goes from 0 to pi over 4, and then a base that goes from pi over 4 to 2 pi over 4. 2 pi over 4 is, of course, pi over 2. And then from 2 pi over 4 to 3 pi over 4, that's the third one. 3 pi over 4 does not simplify. And then the fourth and final one, 3 pi over 4 to 4 pi over 4, and 4 pi over 4 simplifies into pi. So you'll notice here that I've got 4 shapes, and I will concede the point that this first trapezoid is a triangle, but we're just going to call that triangle a, and the word escapes me, which makes sense because I'm recording. Degenerative, that's the word I'm looking for. Took me 5 words to get there, but I got there. Degenerative case of a trapezoid. So I know it's just a triangle, but just pretend it's a trapezoid with this first height of 0. Why is it 0? Because when you substitute 0 into the sine function, you get 0. So the base goes from 0 to pi over 4. See what I've got here in brown. And then the first height goes up to the point when x is 0. And the second height goes up to the point when x is pi over 4. And then I connect those. And that's my first trapezoid. So that's trapezoid 1. Just like my scratch work over here when I was looking at the horizontal axis. Okay, second trapezoid. Second trapezoid goes from pi over 4 to 2 pi over 4 or pi over 2. So the base I draw in right here, and then I've got a height at this point right here, again, sine of pi over 4, and a height at this point right here, sine of pi over 2. So I mark those 2 points in, I draw my heights up, and then I connect them in a diagonal fashion. That's my second trapezoid. Third trapezoid goes from, again, pi over 2, which is 2 pi over 4, to 3 pi over 4. That's the base right there. We get the base sketched in. So get your base sketched in from pi over 2 to 3 pi over 4. The heights that we're going to use are the points at pi over 2, which we already did, and 3 pi over 4, which we're plotting right now. And then we draw from our base the height up on each side, and then connect them in the diagonal fashion like that. So that's a trapezoid with a flat edge on the axis. The fourth and final trapezoid, and yes, I know it's a triangle, just consider it a degenerative case of a trapezoid. And it happens because this height over here is 0. That's the only reason why it's a triangle rather than what looks more like a trapezoid. So just go with it. Goes from 3 pi over 4 to pi. So we put a point at 3 pi over 4. We already made that point. We put a point at pi, because that's our base, and then we draw our heights in up to those points, and then we connect those points in a diagonal fashion. That's what the fourth and final trapezoid looks like. So that should have felt very, very similar to you as when we were doing Riemann sum. We're still working on the axis to get the height, but what's different is instead of saying, am I going on the left, the right, or the middle? When we're doing the trapezoid, we're always going on the left and we're always going on the right. The next thing that's going to be different is the calculations for each one of those trapezoids. Each one of those trapezoids is not base times height because they're trapezoids, not rectangles. Even the degenerative case triangles we're going to treat as trapezoids. So we're going to do the base, which again is going to be that flat edge on the axis times a half, because that's how you find the area of a trapezoid. And then we're going to add the two heights together. So all we're doing is changing around the trapezoidal area formula that you learned back in elementary / middle school, maybe high school. When you learned it is not important. So we're taking those trapezoids that you're used to having, these parallel sides horizontally, and we're doing them this way. Okay, so how do we get the area of that first trapezoid? We're going to do 1/2 times the base times the sum of the two heights. So the first trapezoid starts out just like that. We're going 1/2 times pi over 4. Where did I get pi over 4 from? I got pi over 4 from saying that the x values go from 0, stop at pi, for a total distance of pi. And then we're doing 4 equal-sized base trapezoids. So each one of them is pi over 4. Now, we got to get the two heights. So how do we get the two heights? Well, those are the function values at the point. So I need the function value at the first point at 0 and the function value at the second point, pi over 4. Both of those go into the function formula right here. So we have the sine of 0 plus the sine of pi over 4. That is our first trapezoid. The second trapezoid goes from pi over 4 to pi over 2. That's this trapezoid right here. We're looking at this one. So to do the area of a trapezoid, we do 1/2 times the base. The base is again pi over 4 because we're doing equal bases. The height in each case is the function value, sine of x, at those 2 points. So this left value is again going to be sine of pi over 4. And this right value is going to be at pi over 2, the sine of pi over 2. That is the area calculation for our second trapezoid. 1/2 times base pi over 4 times the sum of the heights at or on sine at pi over 4 and pi over 2 respectively, the left and the right. Okay, third trapezoid. It's going to start off with a 1/2 because 1/2 is part of the formula for finding the area of a trapezoid. Then we multiply by the base. It's a uniform base, so it's the exact same base that we just used for the first two trapezoids, pi over 4. This time, this third rectangle has a base right here, and then the heights are at this point right here at pi over 2, and then on the other side, this point right here at 3 pi over 4. So sine of pi over 2 plus the other height, sine of 3 pi over 4. That was our third trapezoid. I'm going to pause here for questions. Okay, thanks for being a good captain of your own ship and trying out that fourth trapezoidal area. Let's look at it right here, and there's some surprise math. So after you finish checking your trapezoidal area, get in the surprise math. That's new notation we'll be studying in the future. So the fourth trapezoid, area of a trapezoid, 1/2 base times the sum of the heights, 1/2 base pi over 4. First height is the point at 3 pi over 4. Put that into sine because that's the function. Right, that's the function we've got here. Second height at pi, sine of pi. This is approximately equal to this thing right here with a 0 on the top and a pi on the bottom, sine of x dx. So if you have never seen that notation before, that is a definite integral, and we'll be talking a lot about definite integrals in this class moving forwards. Not so much today, but I did want to plant that seed. Little bit of a taste. Okay, so one more thing I want you to do as being the captain of your own ship of the line. I want you to look at some math I've written down for you. And while you're writing this math down, I want you thinking to yourself, what happened here? And I'll be pausing the recording again right here. I'm recording again. Thanks for checking in real quick with your classmates. The way I decided to phrase what happened was I said I factored out the 1/2 and the pi over 4 from each of these 4 terms. And then after factoring those out, I combined like terms. So with the 1/2 times pi over 4, which is pi over 8, I have sine of 0 plus sine of pi over 4 plus sine of pi over 4. There's 2 sines of pi over 4, hence the 2, plus sine of pi over 2 plus sine of pi over 2. There's 2 sines of pi over 2 right there, plus sine of 3 pi over 4 plus sine of 3 pi over 4. That's 2 of those, plus the sine of pi. And graphically, it makes sense because remember, we kept, or for the first and second trapezoid, they overlapped right here on the right side of the first trapezoid and the left side of the second trapezoid, both of them at pi over 4. We did pi over 4 height twice. The second and third trapezoid overlapped right here at pi over 2. On the right side for the second trapezoid, pi over 2. On the left side for the third trapezoid, pi over 2. The third and fourth trapezoid overlapped right here at 3 pi over 4. The right side for the third trapezoid, the left side for the fourth trapezoid, they overlapped right there. So it makes sense that there should be 2 of those inside ones and 1 of those outside ones. Pretty nifty when all of the math stuff makes sense, huh? Yeah, I think so. Now, what we're not gonna do is calculate that because quite frankly, don't care. And also because your brains are reaching about maximum capacity. So we're gonna do one final thing here together. We're gonna look at example 8. Example 8, also in the handout we looked at. We have a table that shows the speed in miles per hour of a cyclist at various times. We're going to use a trapezoidal approximation with 6 subintervals to find the distance in miles the cyclist traveled in the 12-minute time interval. Now there's a couple of ways of doing this one. I'm going to do it one way and tell you about the other way of doing it later. But regardless of those methods, here are 2 really important things I want you to think about. The first thing I want you to think about is your inputs, your axis values. What are they? 0, 2, 5, 6, 9, 10, and 12. If we're doing a trapezoid with 6 subintervals, we're not going to be able to do equal bases again. In order to do 6 equal subintervals, we would have to be able to go from 0 to 12 evenly 6 times, which we cannot using table values. So 0 to 12, 6 equal pieces is 2. We'd have to go 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10, 10 to 12. So we could do some of those, but not all of those. That means we're talking about, that's right, you guessed it, non-uniform bases. Non-uniform bases again. So, second thing that you should always be thinking about when you are looking at doing this type of problem, you could think of it as a Riemann sum type problem, even though it's a trapezoidal problem, is you want to be thinking about your units. Okay, so let's do this one. The input values in the table space out into 6 subintervals. Now they're not equal subintervals, but I could have 0 to 2 be my first subinterval, 2 to 5 be my second, 5 to 6 be my third, 6 to 9 be my fourth, 9 to 10 be my fifth, 10 to 12 be my sixth. So they do space out nicely, even though they're not equal length subintervals or equal length bases or uniform bases. And it says use trapezoidal rule. So we're going to do 1/2 times the base times the sum of the heights for this particular situation. Okay, we got to do this 6 times. So find your strength for a few more minutes of maximum attention. Okay, that first trapezoid is going to have 1/2 times 2. Why does it have 1/2 times 2? Well, it has 1/2 because it's a trapezoid. It has 2 because when you're going from 0 to 2, that's 2 units. The heights are going to be evaluating the function using the table at 0 and evaluating the function at 2. So that's 33 and 25. Check it against the table. The second trapezoid is going to be 1/2 times 3. How come 1/2? Because there's a 1/2 in the area formula for a trapezoid. How come 3? Because if you're going from 2 to 5, that's 3 units. We need the height at 2 and the height at 5. Using the table, the function value at 2 is 25, and the function value at 5 is 27. Okay, 2 down, 4 to go. Next trapezoid. The area is going to be 1/2 times 1 times the quantity of 27 plus 13. Where did I get all those numbers from? The 1/2 is because this is the area of a trapezoid. The 1 is the base length from 5 to 6. 27, that is the function value from the table at 5. 13, that is the function value from the table at 6. Fourth trapezoid. Area formula is going to be a 1/2 times a 3. Why 1/2? Because that's the area formula for a trapezoid. Why 3? Because we're going from 6 to 9. That's 3 units. Please write down what the heights are. I'll pause. Did you write down 13 plus 21? I hope so, because 13 is the function value from the table at 6, and 21 is the function value from the table at 9. Please do the last two trapezoidal areas on your own. I will wait. I'll give you some time. Be a good captain of your ship. Okay, let's check in on those last two trapezoidal areas and finish this sucker off so we can finally put a fork in it and be done. Okay, fifth trapezoid. We use the 1/2. That is the area formula for a trapezoid. You need a 1/2 every single time. The 1, that is the length from 9 to 10. 21, that is the function value at 9. 5, that is the function value at 10. Sixth and final trapezoid, 1/2 times 2 times the quantity of 5 plus 9. How come? 1/2 area formula of trapezoid. 2, base of the trapezoid, because we're going from 10 to 12. 5, how come? Function value at 10 using the table. 9, where did that come from? Function value at 12 using the table. Okay, do some quick computations here. 1/2 times 2 is 1, so we got 1 times 58, which is the sum of 33 and 25. 1/2 times 3 is 3/2. 25 plus 27 is 52. 1/2 times 1 is 1/2. 27 plus 13 is 40. 1/2 times 3 is 3/2. 13 plus 21 is 34. 1/2 times 1 is 1/2. 21 plus 5 is 26. 1/2 times 2 is 1. 5 plus 9 is 14. Multiply, combine. We have 234 mile minutes per hour, which we ought to get rid of. How could we do that? Well, in 1 hour, I believe there are 60 minutes. Yes, no? Yeah. So if we do 234 divided by 60, that should give us the number of miles the cyclist went. So a little bit less than 4. Pretty good. I'm going to assume cyclist is bicycle. So decent bike ride. This was a unicyclist, a very impressive unicycle ride. Which brings me to the last idea about this problem. We could have, from the beginning, changed those minutes into hours, and then we wouldn't be in this position. So I could have done 2 over 60, 3 over 60, 1 over 60, 3 over 60, 1 over 60, and 2 over 60. Okay. We're going to call it there. We have looked at the beginning of the second half of calculus. We've looked at the 3 kinds of Riemann sums. We've talked about uniform bases and non-uniform bases. We've talked about how to do all of those things. We even got a little taste of what we're approximating, the definite integral. The trapezoidal method is more accurate than the rectangular method, but the trade-off is complexity. Something that's really interesting about the trapezoidal method that we're not going to study, but it is interesting, is for the trapezoidal method, it's so precise that we can not only approximate the area pretty closely, there is a formula for the exact area error. So If we wanted, we could calculate the area approximation with the trapezoids. We could determine if it's an over or under approximation, and then using the error calculation for the trapezoidal method, we could figure out exactly how much we're off by and figure out what the exact value is. Now we're not going to do all that, but it's doable. That's how precise the trapezoidal method is. I hope you enjoyed that. I sure did.